All right, so we're going to pick up where we left off in our last recording. So I have made this electric field diagram, constructing it as a replacement for the collection of vectors, electric field vectors that I drew. And my claim was that the field diagram is easier to understand, easier to interpret than a page full of vectors, which I think is true. And let me show you that, but I'm going to show you that by first raising an objection to the field diagram. Since the electric field is a vector field, that means that at every point in space there's an electric field, and therefore at every point in space the field has a magnitude and it has a direction. Well, and using the vectors as an indicator of the electric field at every point in space, so having a page full of vector arrows, is satisfactory in the sense that you know very well that the arrows that we use in the drawings to represent vector quantities automatically carry with them, in a nice, easy to see format, the information about the magnitude and the direction of the vector at wherever you happen to be looking. So for example, right here I drew this vector and say, okay, at this point in space the electric field points that away, and it has a magnitude that corresponds to an arrow of this long, or the length of this arrow corresponds to the magnitude of the field at this point. Whereas over here, its direction is that way, and the magnitude is represented by an arrow of this length, and so on and so on. Okay. It seems right off the top of your head that we have lost that information by drawing these curved field lines rather than the straight field vectors. The directions are okay. The way we interpret this is that at any point on a field line, one of these curves, that the direction of the field at any point is indicated by the tangent of the field curve, the field line at the point of interest. So in other words, right here, the field points in a direction indicated by this arrow, the vector that I drew earlier, and this arrow is tangent to this curved field line. And that was the reason at the end of the last recording that I was at a little bit of pain to relocate my vectors on the field diagrams, because I wanted them to all be tangent to this curved field line at each point. Okay, I didn't want them to cross inside, which was just a mistake of trying to do all this freehand. So the direction is okay, and that's why we put the arrowheads on the curved field lines to indicate the direction of the field points. So we got that. But what about the magnitude? Because after all, I draw this entire curved line here. How can I tell from just looking at this curve, or frankly this curve, how big the field is, what the magnitude of the field is at any of these points? The answer is that we have to reinterpret the meaning of these field lines and reinterpret the indication of magnitude. And it goes simply like this. The magnitude at any point in space, the magnitude of the electric field is indicated by how closely packed together the field lines are. In other words, slightly more formal language, the magnitude of the field at any point in space is indicated in this drawing by the density of the field lines. The more field lines you have packed in to a given area, or more correctly, in a given volume, the stronger the field is at that place. Okay, and so down here, if I were to add a few more, let's just a couple more field lines here, you can see that down here, the field lines are closely packed together. And as a consequence, you interpret the electric field as being stronger in heat in this region than they are up here, for example. Okay, and if I were to draw this a little more carefully, it would look more like that. Okay, so you can see, but the field lines start to get farther apart as you get farther and farther away from the charges, and that indicates that the field is getting progressively weaker and weaker, which of course makes sense. On the other hand, over here, when you're close to the charges, the field lines are very, very closely packed together, indicating a strong field when you're close to the charge, which again should make sense. As you get farther and farther away, the density of the field lines gets smaller and smaller and smaller. The field itself is getting smaller and smaller and smaller. That's where the information about the magnitude of the field is hidden. So hopefully that makes sense. So what I'm going to do now is, once again, I'll do the dipole again without the vectors, and I'll do it a little more carefully this time, and then I'll do one or two other diagrams just to give you the feel for it. And as I say, now, finally, I'm going to go through the rules that you have to follow in in constructing field line diagrams. Okay. So this is going to be a bit boring, as I say, because I've just done the dipole. But the purpose here is to give you the list of rules. Let's see. So let's start with the first. There's no particular order to these rules, other than the order in which I happen to think of them. First rule, when you draw field lines, they must start on positive charges and end on negative charges. Okay. They move away from positive charges. They start on a positive charge, move away, and end on a negative charge. Or they can start or end out to infinity. And I mentioned in a previous recording, obviously we don't draw all the way to infinity. In practice, you draw a few 10 or 20 centimeters if you're on a big chalkboard like this. Okay. Okay, so following that rule here, I will draw a field line, and we'll draw the simple one. I'm going to start it on the positive charge, end it on the negative charge, and we've already talked about the direction, so I won't labor the point, and it points like that. Okay. The next one, I'll draw the next two just above, just below. Starts on the positive charge, ends on the negative charge. Starts on the positive charge, ends on the negative charge. Okay, and the direction arrows are required there. Okay. Well, let me go ahead and then on the other hand, I could have a field line that comes in from infinity, or a field line that goes out to infinity. Starts on the positive charge and goes out to infinity, or comes in from infinity and ends on the negative charge. And that's wrong, by the way. It felt wrong while I was drawing it. we go. That's better. Still feels wrong. What have I done? What have I done wrong? No, I was right the first time. Okay. That's what I did wrong. Okay. No wonder you're confused. Sorry about that. This is what happens when I try to be really careful. So, sorry. I'll give you a secret. So starting on the positive charge, going out to infinity. I'll tell you a secret. How I knew that things were going wrong is because the next couple of field lines that I draw eventually are going to curve around tightly enough that it will start on the positive charge and curve around and end on the negative charge. It'll be a big loop, but they all have to do that. They all have to curve around in a sense that will bring them around to the other charge. And the way I had them curved earlier incorrectly, they couldn't have done that. So I knew something was wrong, and I just had a brain fart. Okay. Start on the positive charge, loop around, end on the negative charge. Start on the positive charge, loop around, end on the negative charge. And always, always put in the direction indicator arrows. This is a little asymmetric. It should be, for this charge distribution, the field line should be symmetric. So, yeah, it's a little better. Okay. And when do you stop drawing field lines? Basically, when you feel like you've made a picture that adequately indicates the electric field, how the electric field is going to behave pretty much everywhere. So in other words, if somebody asks you a question, what is the field doing here? Your diagram is sufficiently detailed to be able to answer that question. Okay, so we started on positive charges, end at negative charges, or start or end at infinity. Great. Okay, rule number 2. Since the magnitude of the fields is indicated by the density of the field lines, as I said a few minutes ago, the number of lines must be proportional to the field strength. In that region. Now, I know this seems a little backwards, perhaps, because you're thinking, well, after all, isn't the field diagram field line diagram supposed to tell you what the magnitude is anywhere? Well, yes, but the diagram is supposed to give you an overall picture and not necessarily enable you to calculate anything at any given point in space. So it's more, if you want, more of a field line diagram is more of a memory jogger than it is a calculation tool. Again, its purpose is to help you visualize what the field looks like. So it's not a one-way street. It's not I draw my field diagram, and from my field diagram I get to figure out what my electric field is, nor is it simply calculate the electric field everywhere in space and then make a diagram of that. It's rather a mixture of both. The process is rather similar to what I did earlier, which was I drew a number of field vectors at a number of selected points, and in a more detailed analysis, I would have actually calculated the field at those various points. And then what I would have done is constructed the field diagram using those several points that I calculated as a guide to diagramming creating the entire field diagram, which is exactly what I did, in fact, except for the calculation part. So the rule that you make sure the number of field lines you draw are proportional to the field strength. The application of that rule, it has to be guided by your knowledge of what the field does at several significant places within the field. Okay. So right. So that's that rule, and basically it goes like this. If you think the field strength is, let us say, twice as large in one area as it is in some other area, then you should have twice as many field lines per square meter, let's say, or per square centimeter in the higher magnitude region than you do in the lower magnitude region. So I think close to the negative charge, the field should have a large magnitude, okay? Whereas the field far away from the well, that was a terrible circle, isn't it? The field far away, relatively far away from the negative charge, should be weaker. And so, man, that's just terrible. Well, anyway, it doesn't matter. Notice that this circle here has a small circumference, and there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, I guess 12 or 13 or 14, whatever it was. I lost count. Let's see. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Yeah, 12. So in this small circle, I have 12 field lines passing through it. Through this larger circle, I also have 12 field lines passing through it. Go ahead and count them. But of course, this larger circle has a much larger perimeter. So although there's the same number of field lines, the number of field lines per total perimeter length is much smaller out here than it is here close to the circle. So the number of field lines in a given area is much larger here than it is out here, and that again is rule number 2 that indicates the field strength in those regions. Okay, and then is simple enough. I don't even have. There's not really much else to draw. Well, let me go ahead and write it down for you. Okay. When you draw your field lines in your diagram, never cross your field lines. The reason for that is simple enough. Each one of these field lines is a vector. Indicates both the magnitude and the direction of the electric field at different points. But what if I were to draw something like that field line? Okay. The problem with this is that at this point right there, the electric field would have 2 different directions. Well, this diagram would be claiming that the electric field points in 2 directions at the same place, which is clearly impossible. That would be very much like saying that if you were moving, that you were moving 2 different directions at once. Now, if for those of you who are trying to be clever, you're saying, but don't you talk about moving in the x direction and the y direction simultaneously? Yes, we talk about that, but that's not what I mean here. I mean, that you would literally be moving in two different directions. You'd be moving north and south at the same time, or you'd be moving north and up at the same time or something. In other words, your body would physically split into two. I don't know. No, it's nonsensical. And so no more can you do that with the field diagram. So the field diagrams, the field lines in a field line diagram must never cross. The only place that they can come together is at the charges themselves, and it's a legitimate question. What happens to the to the electric field exactly at the charges? Because the field line seems to get really large and the area gets really small. So what's going on there? And it's a legitimate question. And if you really want to know the answer, talk to me during class. Okay, so that's the general concepts for drawing a field line diagram. Make sure they never cross. Make sure the field lines start and end on charges, and specifically start on positive charges and end on negative charges, or start at infinity, end at infinity, and make the field line density match the strength of the magnetic field at different points in space. And that's basically it. And follow those rules, and the diagrams will always come out nicely. Okay, so that's that. As to what are we going to do next? Excellent question. I guess you'll have to start the next recording and find out.